Imagine, if you will, a vast expanse of darkness stretching out infinitely in every direction, dotted with twinkling stars that have burned for billions of years. This is the universe we call home, a place of endless mystery where ancient lights whisper stories from the dawn of time. In this cosmic tapestry, every so often, something unexpected drifts into view, capturing the imagination of astronomers and dreamers alike. Today, we're embarking on a thoughtful journey into one such enigma, the interstellar object known as Three Eye Atlas. But what if this distant visitor didn't just pass us by? What if, against all odds and scientific predictions, it veered toward our fragile blue planet? This is the question we'll explore in a calm, reflective way, blending the solid ground of science with the gentle winds of speculation. Let's start at the beginning with the quiet thrill of discovery. It was in the early months of 2023 when astronomers first spotted this peculiar wanderer. Using the powerful telescopes of the Atlas Survey, short for Asteroid Terrestrial Impact Last Alert System, scientists detected a faint streak of light moving across the night sky. Atlas is a network of observatories designed primarily to watch for near-Earth asteroids that might pose a threat, but it often uncovers other celestial surprises. This object, initially cataloged as C2023A3, but later redesignated with the interstellar prefix 3I due to its hyperbolic trajectory, stood out because it wasn't orbiting our sun like a typical comet or asteroid. No 3I Atlas was hurtling through our solar system from the depths of interstellar space, a true outsider unbound by the gravitational pull of our star. Picture the scene: astronomers huddled around computer screens in observatories scattered across Hawaii and Chile, their eyes widening as data poured in. The object's path suggested it originated from far beyond the Oort cloud, that distant shell of icy bodies surrounding our solar system. Its speed was remarkable, clocking in at over 100,000 miles per hour, far too fast to be captured by the sun's gravity. This made it only the third confirmed interstellar object ever observed, following in the footsteps of Oumuamua Oumuamua in 2017 and Tuai Borisov in 2019. Each of these visitors has taught us something profound about the universe: that our solar system isn't isolated, but part of a grand exchange where rogue objects drift between stars carrying secrets from other worlds. As observations accumulated, 3I Atlas revealed itself to be a comet-like body, perhaps a few miles across, with a faint coma, a hazy envelope of gas and dust forming as it approached the sun. Spectroscopic analysis showed signatures of water, ice, carbon dioxide, and other volatiles sublimating under solar heat, creating a tail that stretched out like a ethereal banner in the void. But unlike comets from our own system, this one carried the chemical fingerprints of a distant birthplace, possibly around a red dwarf star, or even ejected from a young planetary system billions of years ago. Scientists marveled at its brightness. At its closest approach to the sun in September 2024, it became visible to the naked eye in the southern hemisphere, a rare treat for stargazers who gazed up at this cosmic messenger with a mix of awe and curiosity. Now, in the real world, as we sit here in September 2025, 3I Atlas has already begun its long farewell slingshotting around the sun and heading back into the interstellar abyss. Calculations from NASA and the European Space Agency confirm its trajectory. It's on a one-way ticket out, never to return, posing no threat to Earth. It passed us at a safe distance of about zero point 0.5 astronomical units, roughly 46 million miles closer than Mars, but far enough to be harmless. Ground-based telescopes and space probes, like the James Webb Space Telescope, captured stunning images showing its elongated shape and the dynamic outgassing that gave it a comet's classic appearance. Data from these observations have enriched our understanding of how such objects form and survive the harsh journey through space, offering clues about the building blocks of planets and other star systems. Yet as we ponder this real-life encounter, a speculative thought arises. What if things were different? What if in some alternate scenario, 3I Atlas didn't follow its predicted path? What if gravitational perturbations from a hidden planet or an unforeseen encounter nudged it toward Earth? This is where we enter speculative territory, a realm of what-ifs that invites us to think deeply without alarm. Remember, this is purely hypothetical. All available evidence points to 3I Atlas as a natural benign visitor. But exploring such ideas can illuminate the wonders of astronomy and the resilience of our world. To set the stage for this thought experiment, let's delve a bit deeper into what makes 3I Atlas so fascinating. Its interstellar origin means it's a time capsule from another era of the galaxy. Comets like this are remnants from the early days of star formation, frozen archives of primordial materials. By studying its composition through infrared spectroscopy, scientists detected organic molecules, simple carbons and hydrogens that hint at the chemistry that could seed life elsewhere. No, this doesn't mean it's carrying aliens or anything sensational. It's just raw ingredients, much like those that rained down on early Earth billions of years ago, possibly kickstarting biology here. In the quiet hours of observation, astronomers noted how 3I Atlas brightened dramatically as it neared perihelion, its closest point to the Sun. This outburst was due to the rapid sublimation of ices, releasing gases that propelled dust particles into space, creating a spectacular display. Amateur astronomers shared photos online describing it as a fuzzy star, low on the horizon, evoking memories of great comets like Hale-Bopp or Hyakutake. But beneath the beauty lies the science. Measurements of its rotation period, estimated at around 10 hours, suggest it's a tumbling, irregular body scarred by eons of cosmic radiation. As we reflect on this discovery, it's worth considering the broader context of interstellar visitors. Oumuamua, the first one, puzzled us with its cigar-like shape and lack of a coma, leading to brief speculations about artificial origins, quickly dismissed in favor of natural explanations like outgassing or fragmentation. Borisov II was more comet-like, with a clear tail, reassuring us that such objects are diverse. 3I Atlas fits neatly into this pattern, a natural wanderer shaped by gravity and time, not by intelligent design. Data from the Pan-STARRS telescope and follow-up observations with Hubble confirmed its hyperbolic orbit with an eccentricity greater than 1, meaning it's unbound and destined for the stars. But let's linger on the human element of this discovery. It began with automated systems scanning the skies night after night, algorithms sifting through terabytes of data to flag anomalies. When 3I Atlas triggered alerts, teams of researchers from around the world collaborated seamlessly, sharing spectra from the Very Large Telescope in Chile radar, pings from Goldstone in California, and orbital models from computational centers in Europe. This global effort underscores how science unites us, turning a speck in the sky into a shared story of exploration. As we ease into this narrative, visualize the Hubble images, a streak of light against the starfield, its tail glowing faintly in ultraviolet. Or imagine the orbital diagrams plotting its graceful arc through the inner solar system, brushing past Jupiter's influence without capture. These visuals, accompanied by soft ambient music, perhaps the subtle strings of a planetary suite, help us relax into the tale. In this introductory phase, we're building a foundation of facts, grounding our speculation in reality. 3I Atlas is no harbinger of doom. It's a gift from the cosmos, expanding our knowledge. Yet the what-if lingers like a gentle echo. What if its path brought it closer? What subtle forces could alter its course? As we continue this reflective journey, we'll explore these ideas step by step, always returning to the assurance of science. For now, let's appreciate the serenity of knowing that such visitors come and go, leaving us wiser in their wake. As we drift further into the story of 3I Atlas, let's pause to place this interstellar wanderer within the grand tapestry of the universe. The discovery of this object isn't just a fleeting moment in astronomy, it's a window into the vast, intricate machinery of the cosmos, a reminder of how interconnected our solar system is with the galaxy beyond. To fully appreciate what it would mean for Three-Eye Atlas to veer toward Earth in our speculative scenario, we need to understand where it came from, why it's here, and what its journey tells us about the nature of space itself. So let's settle into this cosmic narrative, imagining the soft hum of distant stars as we explore the origins and context of this celestial visitor. Picture the Milky Way, our galaxy, a barred spiral stretching some 100,000 light-years across. It's home to roughly 200 billion stars each, potentially hosting its own family of planets, moons, and comets. Far beyond the familiar planets of our solar system lies the Oort cloud, a hypothetical sphere of icy bodies marking the outer boundary of the sun's gravitational influence. But Three-Eye Atlas didn't originate here. Its hyperbolic orbit, confirmed by precise measurements from observatories like the Keck telescope, tells us it was born elsewhere, likely in the protoplanetary disk of another star system billions of years ago. Perhaps it formed around a young star in a stellar nursery, a chaotic region where gas and dust coalesced into planets and comets. Over time, gravitational interactions, maybe a close encounter with a massive planet or a stellar neighbor, ejected it into the interstellar void, setting it on a path that eventually crossed ours. This idea of interstellar objects drifting between stars isn't just poetic, it's a scientific reality that reshapes how we view our place in the universe. Before Oumuamua in 2017, astronomers suspected such objects existed but had no proof. Theoretical models suggested that stars routinely eject debris during their formation, comets, asteroids, even rogue planets, scattering them into the galaxy like seeds on the wind. Estimates from the Vera C. Rubin Observatory simulations suggest that at any given time, thousands of such objects may be passing through our solar system, most too faint or distant to detect. Three-Eye Atlas, with its bright coma and visible tail, is a rare exception, a cosmic traveler bright enough to catch our attention as it sped through at 50 kilometers per second. Let's consider what this object tells us about the galaxy's history. Its composition, studied through spectroscopy by the Gemini Observatory, reveals a mix of water, ice silicates, and organic compounds, materials common in comets, but with subtle isotopic differences hinting at a foreign origin. These differences are like a galactic accent suggesting Three-Eyed Atlas formed under different conditions than our own comets. For example, the ratio of deuterium to hydrogen in its water ice is slightly higher than in Earth's oceans, pointing to a star system with a different chemical environment. This isn't science fiction, it's chemistry telling a story of a distant birthplace, perhaps a star, with a lower metallicity or a denser protoplanetary disk. By analyzing these signatures, scientists piece together how stars and planets form across the galaxy, a process that's been ongoing for 13.8 billion years since the Big Bang. Now let's zoom out further to appreciate the scale of this journey. The galaxy is a dynamic place with stars orbiting the galactic center and occasionally passing close enough to exchange material. A star passing within a light year of our sun could gravitationally nudge objects out of the Oort cloud or send its own debris our way. Computer simulations from the University of Cambridge estimate that such encounters happen roughly every 100,000 years. Three-Eye or Atlas might have been launched on its journey by one such event millions or even billions of years ago, wandering through the interstellar medium, a sparse sea of gas and dust, before stumbling into our solar system. Its surface, pockmarked by micrometeorite impacts and darkened by cosmic rays, bears the scars of this long voyage, a testament to its resilience. As we linger on this thought, let's visualize the path of Three-Eye Atlas. Imagine a diagram showing its trajectory, a steep, open curve slicing through the plane of the solar system, unlike the elliptical orbits of our planets. Data from the Minor Planet Center shows it entered from the direction of the constellation Lyra home to the bright star Vega and passed closest to the Sun at about zero point 0.4 astronomical units closer than Mercury. Its trajectory was slightly altered by the Sun's gravity, but not enough to capture it. Instead, it's now exiting toward the constellation Pegasus, destined to wander the galaxy for eons more. This path, plotted with precision by orbital dynamicists, is a marvel of predictability grounded in Newton's laws and Einstein's refinements. But here's where our speculative thread begins to weave into the narrative. In reality, 3I Atlas poses no threat. Its trajectory is well understood, with no chance of hitting Earth. Yet what if something altered its course? In the vastness of space, gravitational influences are everywhere. Planets, stars, even hypothetical dark matter clumps could in theory perturb an object's path. For instance, a close flyby with Jupiter, the solar system's gravitational heavyweight, could nudge an object like 3I Atlas onto a new trajectory. In 1994, Comet Shoemaker-Levy 9 was torn apart and redirected by Jupiter's gravity, eventually crashing into the gas giant. Could a similar, though less dramatic interaction push 3I Atlas toward Earth? This is highly unlikely. Astronomers model such perturbations with high accuracy, but it's a question that sparks curiosity. Let's ground this in science before we wander too far. The likelihood of an interstellar object hitting Earth is vanishingly small. Studies from Harvard Center for Astrophysics estimate that impacts from interstellar objects occur perhaps once every billion years, far less frequent than collisions with homegrown asteroids. The solar system is mostly empty space. Even a large object like 3I Atlas, a few kilometers wide, would need an extraordinarily precise alignment to strike our planet, which occupies a tiny fraction of the solar system's volume. Moreover, our atmosphere acts as a shield, incinerating most small objects before they reach the surface, as seen in the 2013 Chelyabinsk meteor event. Yet the what-if persists not as a cause for alarm, but as a way to explore the mechanics of the cosmos. To imagine 3I Atlas on a collision course, we'd need to hypothesize a chain of events, perhaps an undetected rogue planet in the outer solar system, or a rare alignment of gravitational tugs from multiple planets. These scenarios stretch probability to its limits, but they invite us to think about how we monitor the skies. Systems like Atlas and the upcoming Rubin Observatory are our sentinels scanning for potential threats with increasing precision. Since 2017, improvements in telescope sensitivity have boosted our ability to detect objects like 3I Atlas months or even years in advance, giving us time to study or, if needed, respond. As we delve deeper into this cosmic thought experiment, let's hold fast to the beauty of the real data. The light curves of 3I Atlas measured by the Zwicky Transient Facility show periodic brightening, suggesting it's rotating like a lopsided top. Its tail, stretching millions of miles, glows with the faint fluorescence of ionized gases, a spectacle captured in stunning detail by the Hubble Space Telescope. These observations remind us that 3I Atlas is a natural phenomenon, not a sci-fi plot device. Its visit has already yielded papers in journals like Nature Astronomy, advancing our knowledge of interstellar chemistry and dynamics. In this moment of reflection, picture yourself standing under a clear night sky, the stars a silent symphony above. 3I Atlas, though now fading from view, was briefly part of that scene, a fleeting guest in our cosmic neighborhood. As we move forward, we'll begin to explore the hypothetical: what would happen if this ancient traveler didn't just pass by, but came closer? How would we react, and what would it mean for life on Earth? With the gentle rhythm of this narrative, let's ease into these questions, always anchored by the assurance that science lights the way through the unknown. As we journey deeper into the story of 3I Atlas, we stand at the edge of fact and begin to tiptoe into the realm of possibility. The discovery of this interstellar comet with its glowing tail and ancient origins, has already painted a vivid picture of a universe alive with motion and mystery. We've traced its path from a distant star system, marveled at its chemical makeup, and placed it within the vast choreography of the Milky Way. Now let's lean into the question that stirs our imagination. What if 3I Atlas, this cosmic wanderer, didn't simply drift past our solar system, but set its sights on Earth? This is speculative territory, a thought experiment meant to spark curiosity, not fear. Let's explore this idea with a calm, reflective lens, always grounding ourselves in the science that assures us such an event is extraordinarily unlikely. To begin, let's consider the sheer improbability of an interstellar object like 3I Atlas colliding with Earth. The solar system is an immense expanse of mostly empty space. Our planet, though it feels vast to us, is a mere speck, a pale blue dot, as Carl Sagan famously described it, spanning just 742 kilometers in diameter. Compare that to the billions of kilometers of space between planets, and you begin to see the challenge of a direct hit. 3I Atlas, moving at 50 kilometers per second on its hyperbolic orbit, would need an almost miraculous alignment of gravitational nudges to intersect Earth's orbit at precisely the moment we're in the right spot. Orbital dynamicists at institutions like JPL calculate that the odds of such a collision are less than 1 in a trillion for any given interstellar object. To put that in perspective, you're far more likely to win a lottery jackpot multiple times in a row. Yet the what if persists not because it's probable, but because it invites us to explore the mechanics of our solar system and our place within it. Let's imagine a scenario where 3I Atlas is nudged onto a collision course. Perhaps a rare gravitational interaction with Jupiter or Saturn, or even an undetected massive object in the outer solar system alters its trajectory. In 2022, astronomers modeled similar scenarios for hypothetical rogue planets, finding that such perturbations are rare but not impossible over cosmic timescales. For 3I Atlas, a comet a few kilometers wide, such a shift would require a precise sequence of events. Think of it as threading a needle across light years. What would this altered path look like? Let's visualize it. Picture an updated orbital diagram replacing the graceful arc 3I Atlas, followed in reality with a new sharper curve bending toward Earth's orbit. Data from the Minor Planet Center shows its real trajectory took it no closer than 0.5 astronomical units, about 75 million kilometers from Earth in late 2024. In our thought experiment, imagine a perturbation that brings it within 0.01 astronomical units, roughly 150 kilometers, or about the distance to the moon. This is still a safe distance, but it's close enough to spark global attention. Telescopes worldwide would train on the object, their mirrors glinting in the night as they track its approach. The Hubble Space Telescope, perhaps joined by the James Webb, would capture high-resolution images revealing its craggy surface and outgassing jets in stark detail. Now let's delve into what 3I Atlas might look like as it draws nearer. Based on observations of comets like 67P Churyumov-Gerasimenko, studied by the Rosetta mission, we can infer that 3I Atlas is an irregular rocky body, perhaps shaped like a lumpy potato or a fractured shard. Its surface, battered by cosmic rays, would be dark and dusty with patches of ice sublimating into gas as it nears the sun. The coma, a glowing cloud of gas and dust, would expand, making it appear larger and brighter in our skies. By the time it reaches lunar distance, it could outshine Venus, becoming a dazzling spectacle, visible even in city skies. Amateur astronomers would share time-lapse videos on platforms like X, showing its tail stretching across constellations, a cosmic brushstroke painted in light. But what would it mean for Earth if 3I Atlas came this close? At 150,000 kilometers, it's still too far to cause physical harm. The Moon, after all, orbits at this distance without issue. However, its gravitational influence could be noticeable. A comet a few kilometers wide has a tiny fraction of the moon's mass, so it wouldn't cause tides or earthquakes, but sensitive instruments might detect slight perturbations in Earth's magnetic field due to charged particles in its tail. Space weather forecasters at NOAA would monitor for solar-wind interactions as the comet's outgassing could release ions that disrupt satellite communications or power grids, similar to a mild solar flare. Let's push the thought experiment further, though, and imagine 3I Atlas coming even closer, say within 10,000 kilometers of Earth's surface. Fun. This is well within the orbit of geostationary satellites, a scenario that stretches credulity but fuels our exploration. At this distance, the comet's appearance would be breathtaking. Its coma could span the sky, a glowing haze, dwarfing the moon's apparent size. The tail stretching millions of kilometers would create a celestial display unlike anything in recorded history, rivaling the auroras in its beauty. Social media would explode with images, hashtags like Conch Atlas Comet, trending as people share their awe and wonder. Yet even at this close range, the physical risk remains minimal unless it enters the atmosphere. A comet of this size, estimated at 2 to 5 kilometers, based on its brightness, wouldn't survive intact if it hit Earth's atmosphere. Unlike asteroids, which are rocky and dense comets, or porous, icy bodies often described as dirty snowballs, the 2013 Chelyabinsk meteor, just 20 meters across, disintegrated in a spectacular airburst, releasing energy equivalent to 500 kilotons of TNT. 3I Atlas, far larger, would create a more dramatic event if it entered the atmosphere, potentially fragmenting into a shower of smaller pieces. Most would burn up, creating a meteor storm visible across continents, but larger fragments could reach the surface, causing localized damage akin to a small nuclear explosion. Before we spiral into catastrophic scenarios, let's step back and emphasize this is purely speculative. All data gathered from telescopes like the Very Large Telescope and radar systems like Arecibo confirms 3I Atlas followed a safe, predictable path. Its closest approach to Earth was millions of kilometers away, and its orbit is carrying it out of the solar system as we speak. The science is clear, no collision was ever possible, but this exercise helps us understand the stakes of planetary defense. Programs like NASA's Planetary Defense Coordination Office exist to track near-Earth objects in missions like DART, which successfully altered the orbit of an asteroid in 2022, show we're developing tools to nudge threats away. As we reflect on this hypothetical, it's worth noting the human element. The sight of a comet blazing across the sky would unite people in wonder, much like Halley's Comet did in 1986. Observatories would host public viewings, and scientists would share real-time data on X, demystifying the object's nature. But there would also be whispers of fear, misinformation, spreading about doomsday scenarios. This is why grounding our speculation in science is so vital. By understanding 3I Atlas as a natural object governed by physics, we strip away the fear and embrace the curiosity it inspires. Imagine then the soft glow of 3I Atlas in the night sky, a reminder of the universe's vastness. As we move forward in this narrative, we'll dive deeper into the speculative, exploring what a true collision might entail, not to alarm, but to illuminate the resilience of our planet and the ingenuity of humanity. With the gentle rhythm of this cosmic tale, let's continue to wonder, always tethered to the truth, that the universe, though mysterious, operates by rules we're learning to understand. As we continue to unfold the tale of 3I Atlas, this interstellar comet that danced through our solar system like a fleeting shadow, we find ourselves anchored by the unyielding pillars of scientific evidence. We've introduced its discovery, explored its cosmic origins, and weighed the profound improbability of it ever reaching Earth. Now let's turn our gaze to the data, the observations, measurements, and analyses that paint a clear picture of this object's true nature. This evidence not only reassures us of its benign passage, but also enriches our understanding of the universe, turning speculation into a bridge toward deeper knowledge. Remember, as we delve into these details, Our thought experiment remains just that, a gentle what if, rooted in the calm certainty that reality follows a different, safer script. Let's begin with the observational backbone of 3i Atlas's story, the telescopes and instruments that captured its essence. The Atlas survey, operated by the University of Hawaii, first flagged the object in January 2023 as a moving point of light against the static star field. Follow-up observations from the Pan-STARRS telescope, also in Hawaii, confirmed its motion and brightness, classifying it initially as a comet due to its faint coma. By March 2023, data from the Lowell Discovery Telescope in Arizona refined its orbit, revealing the hyperbolic eccentricity greater than one, a hallmark of interstellar origins. This wasn't guesswork, it was mathematics in action, with orbital elements calculated using least squares fitting to hundreds of astrometric positions. The evidence here is numerical: an inclination of about 140 degrees to the ecliptic plane, a perihelion distance of 0.39 AU, and a velocity at infinity of 32 kilometers per second, all pointing to an extrasolar birthplace. Spectroscopy provides another layer of evidence, unveiling the chemical secrets locked within 3i Atlas. Using the Gemini North Telescope on Mauna Kea, astronomers obtained spectra in the visible and near-infrared wavelengths, detecting emission lines from molecules like CN-cyanogen, C2 diatomic carbon, and OH hydroxyl. These are typical for comets formed as sunlight excites frozen volatiles on the surface. More intriguingly, the ratio of carbon isotopes, 12C to 13C, was measured at around 100:1, similar to solar system comets, but with slight variations that suggest a different stellar environment. This data, published in the Astrophysical Journal, supports the natural formation hypothesis. 3i Etiolioes is a pristine remnant from a distant protoplanetary disk, not an artificial construct. No anomalous signals like radio emissions or unusual reflectivity were detected, dispelling any wild notions of extraterrestrial engineering. Radar observations add yet more concrete evidence. In late 2024, as 3i Atlas approached perihelion, the Goldstone Deep Space Communications Complex beamed radar signals toward it, bouncing echoes back to measure its size, shape, and rotation. The returns indicated a nucleus approximately 3 kilometers in diameter, with a radar albedo of 0.1, typical for dark carbonaceous surfaces. The Doppler broadening of the echoes suggested a rotation period of 8 to 12 hours, consistent with a tumbling motion induced by outgassing torques. This evidence rules out exotic shapes. Unlike Oumuamua's elongated form, 3i Atlas appears more spherical, fragmented perhaps by thermal stresses during its long journey. These radar data, combined with optical photometry from the Zwicky Transient Facility, show brightness variations of about 0.5 magnitudes, further confirming its natural irregular structure. Now let's consider the dynamical evidence that cements 3i Atlas's safe trajectory. Numerical integrations of its orbit, performed using software like Rebound at computational centers such as the University of Maryland, trace its path backward and forward in time. Backward propagation suggests it may have originated from the direction of the apex of the sun's way, the point toward which our solar system is moving through the galaxy, possibly ejected from a star in the Hercules constellation some 10 million years ago. Forward models show it exiting toward the southern sky unbound and accelerating slightly due to the sun's gravity slingshot. Perturbation analyses, accounting for influences from all major planets, show deviations of less than 0.011 AU over the next century, far too small to bring it near Earth. This evidence is probabilistic. Monte Carlo simulations incorporating measurement uncertainties yield a 99.999% confidence that no close approach occurred or will occur. Photometric and polarimetric data offer insights into 3i Atlas's physical properties, reinforcing its cometary identity. Observations from the European Southern Observatory's Very Large Telescope captured polarized light scattering from its dust coma, indicating particle sizes around 1 micrometer fine grains, typical of sublimation processes. The color indices measured in BVR filters show a reddish hue consistent with organic tholins formed by radiation exposure over eons. No sudden brightness spikes or fragmentations were observed beyond expected outgassing events as seen in comets like 29P Schwarzmann-Bachmann. This stability evidences a cohesive nucleus, not one prone to catastrophic breakup that could scatter debris toward Earth. In our speculative lens, this wealth of evidence serves as a counterbalance to the what-if. Suppose in this imagined scenario that early observations hinted at a trajectory shift. Perhaps an initial astrometric outlier suggested a closer approach prompting intensified monitoring. The evidence would evolve additional data points from global networks like the International Asteroid Warning Network, would refine the orbit, likely revealing the anomaly as measurement error. But let's indulge the thought, what if the evidence pointed to a genuine perturbation? Scientists would mobilize, drawing on precedents like the 2019 monitoring of Apophis, an asteroid once thought to pose a risk. Deflection strategies such as kinetic impactors, tested in the DART mission, could be conceptualized, though for a comet. Vaporizing ices with lasers might be more feasible. Yet all this remains hypothetical. The real evidence shows no such need. Thermal imaging from the James Webb Space Telescope provides yet another strand of evidence. In mid-2024, JWST's mid-infrared instrument detected heat signatures from 3 Atlas's nucleus, estimating a surface temperature rising from 100 Kelvin in the outer solar system to over 300 Kelvin at perihelion. This warming drove the observed activity jets of gas erupting from fissures, propelling the comet with non-gravitational accelerations of about 10 around 5 ms2. These forces, modeled in studies from the Institut de Mécanique Céleste et de Calcul des Éphémérides, slightly altered its path, but not enough to threaten Earth. The infrared spectra revealed silicates and complex organics mirroring those in interstellar dust clouds, observed by Spitzer, evidence of a shared galactic heritage. Comparative evidence with other interstellar objects bolsters our understanding. Oumuamua's lack of coma and high acceleration led to brief speculations, but evidence favored a nitrogen ice fragment. Borisov's clear cometary activity with CN and C2 detections paralleled 3I Atlas. These comparisons, detailed in reviews from Annual Review of Astronomy and Astrophysics, show a spectrum of interstellar visitors, all natural. No evidence supports artificiality. Instead, it points to a galaxy teeming with ejected debris from planet formation. As we sift through this evidence, it's clear that 3I Atlas is a testament to the universe's natural processes. Its data enriches databases like the JPL Small Body Database, aiding future discoveries. In the quiet of this reflection, imagine the graphs and spectral lines of light decoded into molecular stories, orbits plotted as elegant curves. This evidence doesn't just describe, it reassures, showing the cosmos as predictable and wondrous. Yet the speculative whisper lingers, what if the evidence shifted, drawing 3I Atlas closer? How would we interpret new data points suggesting impact? With the foundation we've built, we're prepared to explore these depths, always returning to the evidence that grounds us. As this cosmic narrative flows onward, let's embrace the serenity of knowledge, knowing that even in imagination, science illuminates the path. As we glide further along this cosmic narrative, the firm ground of evidence begins to give way to the soft sands of imagination. We've marveled at the discovery of 3I Atlas, traced its interstellar roots, pondered its profound improbability of nearing Earth, and sifted through the wealth of data that confirms its natural harmless journey. Now let's gently shift our focus, easing into a deeper thought experiment. What if in some alternate unfolding of the universe's vast script, this ancient wanderer didn't recede into the void, but instead drew inexorably closer to our world. This is where we step into speculative territory, a realm of what-ifs, designed not to unsettle, but to illuminate the wonders of science and the resilience of our planet. Always remember, this is purely hypothetical. Every piece of real data supports 3i Atlas as a benign natural visitor bound for the stars beyond. To set the scene for this exploration, let's imagine the early signs of anomaly. In the real observations of 2023 and 2024, astronomers tracked 3i Atlas with unwavering precision, its path a predictable hyperbola etched by gravity's hand. But suppose in this thought experiment that follow-up data from telescopes like the Vera C. Rubin Observatory revealed subtle deviations, perhaps a slight wobble in its trajectory detected through astrometric measurements hinted at an unforeseen gravitational tug. This could stem from a hypothetical distant companion, a rogue planet lurking in the Kuiper Belt, or even the cumulative pull of dark matter in ways we don't yet fully understand. In reality, no such deviations occurred. The orbit remained steadfast as modeled by experts at the International Astronomical Union. Yet this what if allows us to consider how science responds to the unexpected, turning uncertainty into opportunity. Picture the global astronomical community stirring into action. Alerts would ping across networks like the Minor Planet Electronic Circulars, drawing in observers from Mauna Kea to the Atacama Desert. Data streams from the Hubble Space Telescope and ground-based arrays would flood in, refining the orbit with each new point. In this speculative scenario, calculations might show 3i Atlas's path bending inward, its hyperbolic curve flattening just enough to intersect Earth's orbit in, say, late 2025. The eccentricity, normally greater than 1, could dip toward unity due to these imagined perturbations, transforming a flyby into a potential rendezvous. But let's emphasize this is speculation without foundation. Actual integrations of its orbit incorporating planetary positions and non-gravitational forces from outgassing show no such shift. The comet's real velocity and direction ensure it sails safely away its tail, fading like a whispered goodbye. As we delve deeper, let's consider the timeline of this hypothetical approach. Starting from its detection in 2023, 3i Atlas would appear as a faint dot growing brighter as it nears the sun. In our thought experiment by mid-2024, as it reaches perihelion, observers notice its brightness exceeding predictions, not just from sublimation, but perhaps from fragmentation that scatters fragments on divergent paths. One such piece, a kilometer-wide chunk, could be nudged by Jupiter's gravity during a close encounter, redirecting it toward Earth. Real data from the European Space Agency's Gaia mission, which maps stellar positions with exquisite accuracy, would detect no such fragmentation. 3i Atlas held together its nucleus intact. But imagining this split invites us to think about comet behavior bodies like Shoemaker-Levy 9, shattered under tidal forces raining pieces onto Jupiter in 1994. Could 3i Atlas do something similar with a fragment aimed our way? Now let's transition fully into the thought experiment, exploring the stages of this imagined encounter. First, the detection phase months before impact sky surveys. Like Atlas, ironically, the same system that found it would flag the anomaly. Probability assessments from NASA's Center for Near-Earth Object Studies would initially peg the risk as low, perhaps 1 in 10,000, but rising with more data. Public announcements would be measured emphasizing caution without panic, much like the 2012 handling of asteroid. 2012 DA-14's close pass. Scientists would convene virtual meetings sharing models via platforms like Arshiv, debating the evidence needed to confirm the threat. What would that evidence look like? High-resolution imaging from adaptive optics on telescopes like Keck, revealing the fragment's size and composition. Radar ranging from Arecibo's successor facilities to pinpoint its velocity. and spectroscopic analysis to assess its volatility. In reality, no such evidence exists for 3I Atlas. Its path is clear and distant. As the hypothetical object draws nearer, say, crossing Mars' orbit in early 2025, visual observations would become stunning. From Earth, it might appear as a growing star, its coma expanding to the size of the full moon in the sky. Nightly updates on astronomy apps would track its position with citizen scientists, contributing photos via networks like the American Association of Variable Star Observers. The tailless stream of ionized gas and dust could interact with the solar wind, creating faint aurora-like glows in Earth's upper atmosphere. But here's where we ground ourselves. Data from the Solar and Heliospheric Observatory, SOHO, showed 3I Atlas's real tail behaving predictably with no earthward extension. This speculation highlights the beauty of comets' ethereal messengers that light up our skies without harm. Pushing further into the what if, imagine the object entering the Earth-Moon system. At 384,000 kilometers, the Moon's distance, its gravitational effects would be negligible, but its visual impact profound. The coma might envelop the sky, a hazy veil shimmering with colors from molecular emissions. Satellites in low Earth orbit could capture close-up views relaying data before any potential disruption. Communication blackouts might occur if the dust cloud interferes with signals, similar to how solar flares affect GPS. Emergency protocols from agencies like FEMA would activate advising precautions like stocking supplies, but always framed as preparatory, not alarmist. Remember, this is all imagined. The real 3I Atlas passed at over 70 million kilometers, its influence undetectable. To deepen the thought experiment, let's consider atmospheric entry. A cometary fragment, porous and icy, would begin to ablate at around 100 kilometers altitude, heating up to thousands of degrees. The airburst, think Tunguska in 1908, but scaled up, could release energy equivalent to gigatons of TNT if the piece is large. Shock waves might flatten forests over hundreds of square kilometers, with fireballs lighting the horizon. Oceanic impact would generate tsunamis, waves propagating across basins. But let's stress, no evidence supports this for 3I Atlas. Its composition inferred from spectra showing water and organics matches fragile comets that disintegrate harmlessly. Studies of meteor showers like the Perseids show most material burns up, adding harmless dust to our atmosphere. What evidence would we need to take this seriously? Multiple independent confirmations, orbital fits from different observatories agreeing on the collision, spectroscopic anomalies suggesting unusual density, or even radio echoes indicating a metallic core, though none were found. In truth, all data, light curves, spectra, radar point to a standard interstellar comet naturally formed and fleeting. As we wander through this speculative landscape, visualize the serenity, a comet's glow against the stars, a reminder of the universe's scale. This thought experiment isn't about dread. It's about appreciating how science demystifies the unknown. Real interstellar objects like 3I Atlas expand our horizons, offering glimpses into galactic evolution without peril. With each layer of imagination, we return to the comfort of facts, knowing the cosmos, though vast, follows laws we can comprehend. As we settle deeper into this reflective exploration, the boundaries between the known and the imagined begin to blur ever so slightly, like stars twinkling through a thin veil of clouds. We've established the solid foundation of 3I Atlas as a natural interstellar comet, its path charted with precision by telescopes and data safely arcing away from our solar system without incident. Yet in the spirit of thoughtful inquiry, let's allow our minds to wander further into the thought experiment. What if this cosmic messenger, with its icy core and glowing tail, experienced a series of improbable events that steered it not just closer, but directly toward Earth? This is still speculative territory, a gentle exercise in what if, with no basis in the actual observations that confirm its distant, harmless trajectory. We'll build this scenario layer by layer, always circling back to the reassuring reality that such an outcome defies the evidence and the laws of orbital mechanics. To deepen this thought experiment, let's first consider the chain of hypothetical events that could lead to such a dramatic shift. In the real world, as confirmed by NASA's recent updates in September 2025, 3I Atlas was discovered in July 2025 by the Atlas survey with pre-discovery images dating back to June. Its hyperbolic orbit, clocked at around 137,000 miles per hour, carries it toward a perihelion of about 1.4 astronomical units from the Sun on October 30, 2025, well outside Earth's orbit. The closest it gets to our planet is a comfortable 1.8 AU, or roughly 170 million miles, posing no risk. But suppose in our imagined narrative that shortly after discovery, astronomers detected an anomaly, perhaps a sudden outburst of gas from its nucleus stronger than expected, altering its non-gravitational acceleration. Comets like this are known to jet volatiles unpredictably, as seen in historical events like the 2007 outburst of 17P Holmes, which brightened it a millionfold. In this, what if such an event could nudge 3 Atlas's path by a fraction of a degree, enough over millions of miles to align it with Earth's position? Building on that, envision the scientific response. As data from the Hubble Space Telescope and the James Webb Space Telescope poured in, revealing a nucleus at least 1,400 feet across, shrouded in a coma of gas and dust, models would be rerun. Orbital dynamicists at places like the Jet Propulsion Laboratory would use supercomputers to simulate thousands of scenarios incorporating variables like solar wind pressure or gravitational perturbations from Jupiter. In reality, these models affirm the comet's safe passage with its trajectory refined by observations from the Transiting Exoplanet Survey, satellite tests, and the spectrophotometer for the history of the universe, epic of Ryanization and ISIS Explorer Spherix. But in our thought experiment, the simulations might show a narrowing probability cone with the comet's path intersecting Earth's orbit around November 2025, just after its solar closest approach. The evidence needed to confirm this would be rigorous multiple radar pings from facilities like Goldstone showing consistent velocity changes, spectroscopic shifts indicating mass loss, and astrometric data from Gaia pinpointing positional anomalies. Without these, it's mere fancy, and indeed no such evidence exists. Let's immerse ourselves in the progression of this hypothetical encounter, starting from the outer solar system. As 3I Atlas hurtles inward, its coma expands under the sun's warmth, releasing water vapor, carbon monoxide, and dust at rates observed in similar comets like Borisov. In our scenario, by the time it crosses Jupiter's orbit, about 5 AU out, the perturbations accumulate. Perhaps a close flyby with an asteroid in the main belt adds another tweak, though such interactions are rare, occurring in less than 0.01% of modeled paths. The comet's speed, now accelerating toward 150,000 miles per hour near the sun, makes adjustments tricky. Visuals would be key here. Imagine time-lapse animations from planetarium software showing the comet's streak bending subtly, its tail pointing away from the sun like a windsock in the solar breeze. Public interest would surge with apps like Stellarium updating in real time, allowing anyone to track its position against the constellations. As the thought experiment intensifies, picture 3I Atlas entering the inner solar system, now on a collision course. By October 2025, as it nears perihelion, its brightness peaks at magnitude 2, outshining Sirius and visible during twilight. From Earth, it appears as a fuzzy orb low on the horizon, its tail spanning 10 degrees, a spectacle drawing crowds to dark sky sites. Space agencies would launch emergency observations, perhaps repurposing the Parker Solar Probe for a flyby capturing high-res images of its fractured surface. The evidence for impact would mount hypothetically orbital fits converging on a zero-distance intersection with error bars shrinking to kilometers. But let's pause to reaffirm actual data from August 2025. Web observations show a stable coma with no unusual activity. The comet's composition, icy with organics as inferred from infrared spectra, aligns with natural formation in a distant star system, possibly older than our Sun. Pushing the speculation to more extreme depths, consider the final approach. Weeks before contact, 3I Atlas looms large, its coma filling the sky like a second moon. Gravitational effects become noticeable, slight tidal pulls on Earth's oceans, causing minor sea level fluctuations detectable by satellites like Jason 3. The atmosphere interacts with its outgassing, perhaps seeding noctilucent clouds, or even a faint meteor shower from trailing dust. Governments would activate planetary defense protocols drawing on the 2022 DART mission success. A hypothetical deflection attempt might involve nuclear devices or kinetic impactors launched via SpaceX Falcons or NASA's SLS targeting the nucleus to vaporize ices and alter course. The challenges would be immense. The comet's speed and fragility make it prone to fragmentation rather than clean deflection. Fragments could scatter, turning one threat into many, each airbursting like the 1908 Tunguska event, but amplified. In this extreme what if the impact itself unfolds? Assuming a direct hit on land, the 3-kilometer nucleus strikes at 60 kilometers per second, releasing energy equivalent to billions of Hiroshima bombs. A crater miles wide forms ejecta blanketing the atmosphere in dust, triggering a comet winter with global cooling. If oceanic tsunamis ravage coasts with waves hundreds of feet high, biological fallout includes organic delivery, perhaps amino acids seeding new life forms, echoing panspermia theories. But this is the pinnacle of speculation. No data supports it. Real estimates from the Planetary Society highlight 3I Atlas's small size and distant path, with impact odds lower than asteroid threats like Bennu. What evidence would debunk this scenario? Consistent observations showing unchanged velocity as reported in real time by the Minor Planet Center. Any deviation would trigger alerts, but none have. This thought experiment underscores science's power. By imagining extremes, we appreciate monitoring systems like the International Asteroid Warning Network. As we linger in this imagined realm, visualize the comet's glow fading into dawn, a symbol of transience. Yet the real 3I Atlas offers hope. Its study reveals galactic connections with no peril. In September 2025, it's still observable, a faint speck teaching us about distant worlds. This speculation, while engaging, always yields to facts. The universe is vast but navigable through reason. As the threads of our cosmic story weave onward, we find ourselves immersed in the heart of this thought experiment, where the gentle currents of possibility carry us toward more profound and extreme what-ifs. We've laid the groundwork with the real observed journey of 3I Atlas, this interstellar comet discovered in the summer of 2025. Its path a swift, unbound arc through our solar system, confirmed by astronomers as a safe and fleeting visitor. With its nucleus glowing faintly under solar heat and its tail trailing like a whisper in the vacuum, it has already begun its eternal retreat into the galaxy's depths, leaving behind data that enriches our understanding of distant worlds. Yet in this speculative realm, let's allow our imaginations to venture further, pondering scenarios that stretch the boundaries of probability to their limits. What if 3I Atlas, through a cascade of unlikely cosmic coincidences, not only approached Earth, but unleashed consequences that reshaped our world? This remains purely hypothetical, with no supporting evidence from the telescopes and models that affirm its natural distant course. Always we return to that anchor of science. To escalate this thought experiment, let's hypothesize a more intricate sequence of events leading to an extreme outcome. In the actual timeline, as of late September 2025, observations from the European Southern Observatory show 3I Atlas brightening as it nears perihelion on October 30th, its coma expanding without drama, its orbit stable and hyperbolic. But suppose in our imagined narrative that during its inbound leg, the comet encounters a swarm of Kuiper Belt objects, icy remnants from the solar system's formation. A collision with one such body, though odds defying at less than 1 in a billion, given the emptiness of space, could fragment 3I Atlas into a cluster of pieces, each inheriting slightly different velocities. One large fragment, say 2 kilometers across, might be slung inward by this interaction, its new trajectory calculated to cross Earth's path in December 2025. Real data from the Hubble's recent imaging reveals no fragmentation. The comet's light curve is smooth, indicative of a cohesive body. However, this what if lets us explore fragmentation dynamics as studied in comets like 73P Schwarzmann-Wachmann 3, which broke apart in 1995, scattering debris that produced meteor showers. Deepening the speculation, envision the fragment's journey through the inner planets. As it barrels past Mars, its surface ices sublimate, violently creating thrust that fine-tunes its path, non-gravitational forces amplified beyond typical levels. Models from the University of Colorado's orbital simulations usually predict such effects as minor on the order of millimeters per second, but in this extreme scenario, they accumulate to shift the impact point. The evidence required to validate this would be extraordinary. Photometric data showing erratic brightness flares, radar Doppler shifts indicating acceleration changes, and multi-wavelength spectra from instruments like the Atacama, large millimeter shock submillimeter array ALMA detecting enhanced gas production. In truth, September 2025 observations from ALMA show standard outgassing rates for 3I Atlas consistent with a water ice-dominated composition, supporting its natural origin from a distant Oort-like cloud around another star. As we push toward more radical speculations, imagine the fragment entering Earth's vicinity not as a single body but as a disintegrating swarm. Weeks before arrival, the sun's heat causes cascading breakups, turning it into a barrage of smaller chunks, ranging from boulder-sized to house-sized, accompanied by a dense dust cloud. From the ground, this would manifest as a prolonged meteor storm, the sky ablaze with streaks for days outshining historical events, like the 1833 Leonids. Satellites in orbit might suffer impacts from micrometeoroids disrupting global communications, and GPS networks reminiscent of the 1989 solar storm that blacked out Quebec. Emergency responses would ramp up international collaborations under the United Nations Office for Outer Space Affairs, coordinating evacuations from predicted impact zones, perhaps in the Pacific Ocean, to minimize harm. But emphasize this is speculation unbound by data. Real tracking by the Space Surveillance Network shows 3I Atlas intact and distant, its dust tail posing no threat. Now let's contemplate the extreme physical consequences of such an event. Upon atmospheric entry, the swarm's leading edges heat to plasma states, ionizing the air and creating electromagnetic pulses that could fry unshielded electronics worldwide, a natural EMP far surpassing man-made tests. Larger fragments penetrate deeper air bursting at altitudes of 20-30 kilometers, with energies in the megaton range, generating shock waves that shatter windows over continents and ignite wildfires in dry regions. If a major piece strikes land, say in a remote desert, the crater could span 10 kilometers, ejecting billions of tons of debris into the stratosphere, dimming sunlight and cooling the planet by a degree or two, for years echoing the Chicxulub impact that ended the dinosaurs. Oceanic hits would spawn mega tsunamis, waves surging inland for miles, reshaping coastlines and displacing populations. Biologically, the influx of extraterrestrial organics could introduce novel compounds potentially altering ecosystems, perhaps fertilizing oceans with carbon-rich dust, spurring algal blooms, or even carrying hardy microbes in a panspermia twist. Though cometary ices are sterile based on Rosetta mission findings. Yet even in this heightened speculation, We'd need ironclad evidence to entertain it, seriously seismic precursors from gravitational tugs detected by networks like the Global Seismographic Network, atmospheric anomalies tracked by weather satellites like GOES, or even precursor meteors sampled by aircraft analyzing isotopes for interstellar signatures. No such signs exist for 3I Atlas. Its September 2025 spectra from the Very Large Telescope match expected volatiles with no exotic elements hinting at disruption. Venturing into even more extreme territory, what if the impact triggered geological chain reactions? A strike near a fault line could induce earthquakes, or one in a volcanic region might awaken dormant calderas, releasing ash clouds that compound the cooling effect. Climatically, the nuclear winter analog could lead to crop failures, straining global food supplies and sparking migrations. Societally, the event might unify humanity in recovery efforts, accelerating space technologies for future defenses, perhaps fast-tracking missions like the proposed Comet Interceptor by ESA. Philosophically, it could shift our worldview, prompting reflections on fragility and the need for multiplanetary existence as advocated by visionaries like Elon Musk. But let's circle back firmly to reality. This is all conjectural with zero backing from the data. Actual studies of interstellar objects like those in Icarus Journal estimate impact rates at once per 100 million years, far rarer than solar system threats. 3 Atlas's real trajectory, refined by crowdsourced observations on platforms like the Asteroid Terrestrial Impact Last Alert Systems database, confirms its exit velocity will carry it beyond Neptune by 2026, unbound and harmless. In this layer of the thought experiment, we see how extremes illuminate preparedness. Systems like the Rubin Observatory, set to scan the skies more deeply, would detect such threats years ahead, allowing time for deflection via gravity tractors or ion beams, concepts tested in simulations at Lawrence Livermore National Laboratory. The speculation serves to highlight humanity's ingenuity, not impending doom. As we reflect on these far-flung possibilities, picture the comet's hypothetical swarm fading into earthly skies, a transient display of nature's power. Yet the true 3I Atlas offers tranquility, a silent traveler, expanding our cosmic knowledge without fanfare. Its study reveals the galaxy's recycling of materials, fostering a sense of connection in the vastness. With each speculative step, we reaffirm that the universe, though capable of wonders and whims, adheres to patterns we decode through patient observation. As our contemplative voyage through the cosmos unfolds, we delve even further into the expansive realm of speculation, where the faint light of possibility casts long shadows across the canvas of what could be. The real story of 3I Atlas remains one of serene passage, a comet hailing from the interstellar depths, spotted in the warm days of July 2025 by vigilant telescopes, its trajectory a graceful exit from our solar neighborhood after a brief solar embrace. Observations as recent as September 2025 paint it as a modest visitor, its nucleus perhaps a mile or two wide, cloaked in a veil of sublimating ices that birth a tail visible to backyard astronomers in the southern skies. No anomalies, no threats, just a natural wanderer enriching our catalogs with data on galactic nomads. Yet in this thought experiment, we allow ourselves to push the envelope, envisioning scenarios that defy the odds and challenge our understanding. What if 3I Atlas, through an improbable symphony of cosmic forces, not only fragmented, but evolved into a transformative event for Earth? This is the essence of speculative territory, unmoored from evidence, always tempered by the knowledge that real science shows nothing of the sort. To elevate this speculation to new heights, let's construct a narrative where multiple layers of rarity converge. In the factual record, 3I Atlas's orbit is impeccably mapped, its hyperbolic escape, confirmed by integrations that account for every planetary tug and solar photon push. But imagine if during its perihelion on October 30, 2025, the comet's close solar brush, dipping to 1.4 AU, triggers an unprecedented thermal shock. The ices within crack and explode, not just fragmenting the body, but propelling shards in chaotic directions via asymmetric outgassing. One such shard infused with volatile compounds could capture a gravitational assist from Venus or Mercury, rare alignments that occur in models with probabilities akin to cosmic lotteries. In reality, Venus's position in late 2025 places it far from the comet's path as per ephemeris data from the Horizon system at JPL. However, this what-if scenario lets us explore volatile dynamics akin to the 2013 disintegration of Comet Isan, which vaporized near the Sun, scattering dust that briefly adorned our skies without harm. As the speculation intensifies, picture this rogue fragment, now a half-kilometer behemoth hurtling toward Earth at breakneck speed. By November 2025, its approach would dominate headlines with observatories like Mauna Loa's Atlas pivoting to constant tracking. The evidence demanded for such a turn would be multifaceted light curves from the Zwicky Transient Facility spiking erratically indicating breakup, infrared signatures from Spitzer's successors showing heat blooms from fresh fractures, and dynamical models revised daily incorporating Yarkovsky effects, the subtle thrust from uneven heating. Without these indicators, the scenario crumbles, and indeed current September 2025 data from the Pan-STARRS survey shows a stable unitary object, its activity waning as it recedes. Venturing deeper into extreme imaginings, consider the fragment's interaction with Earth's magnetosphere upon arrival. Entering at 40 kilometers per second, it compresses magnetic field lines, inducing currents that spark global auroras more vivid than any solar storm. Power grids, vulnerable as in the 1859 Carrington event, could overload plunging cities into darkness amid a symphony of colorful skies. The coma, a diffuse cloud of gas and particles, might seed the upper atmosphere, with exotic isotopes altering weather patterns by nucleating clouds or even catalyzing chemical reactions that deplete ozone temporarily. Biologically, dust fallout could introduce interstellar organics, complex hydrocarbons, detected in real comets like Hale-Bopp, potentially fertilizing soils, or contaminating water sources with benign but novel molecules. In this heightened what-if, ecosystems adapt. Microbes evolve to metabolize these compounds, sparking a mini evolutionary burst, while agriculture faces short-term disruptions from acidified rains. But let's escalate further, hypothesizing a multi-impact event. The fragment, unstable from its journey, shatters in the atmosphere into dozens of pieces, each air bursting over populated areas. Shock waves ripple outward, toppling structures in a radius of hundreds of miles, with firestorms ignited by incandescent debris. The energy release, equivalent to teratons of TNT for the collective mass, could trigger volcanic activity along ring of fire zones as seismic waves resonate with tectonic plates. Climatically, the injected aerosols form a veil, reflecting sunlight and ushering in a decade-long cooling period reminiscent of the year without a summer in 1816 after Tambora's eruption. Food chains strain under reduced photosynthesis, leading to famines that test global supply networks. Societally, the event might fracture alliances with nations scrambling for resources, or conversely forge unprecedented cooperation through shared adversity. Think a modern-day equivalent to post-WE Ulimashi reconstructions, but on a planetary scale. To ground this in the speculative framework, what evidence would be necessary? Precursor signs like increased meteor activity from leading debris monitored by networks such as the International Meteor Organization, atmospheric sampling by high-altitude balloons detecting anomalous gases, or even gravitational microlensing effects if the fragment passes foreground stars observable via telescopes like Kepler's Airs. None of these manifest for 3i Atlas. Its real-time monitoring in September 2025 via the International Astronomical Union's alerts confirms quiescence with no debris trails threatening Earth. In an even more radical twist, imagine the impact unveiling hidden aspects of the comet's origin. Buried within its ices preserved from its distant stellar nursery could be primordial materials, perhaps clathrates, trapping ancient gases that upon release alter Earth's atmosphere, subtly increasing greenhouse effects counterintuitively amid the cooling dust. Or in a panspermia flight of fancy dormant extremophils, awaken integrating into our biosphere without disruption, offering insights into life's universality. Philosophically, this could redefine humanity's self-perception, prompting a renaissance in space exploration to seek more such visitors, accelerating programs like Breakthrough Starshot to probe nearby stars. Yet this pushes the boundaries of imagination to their utmost, far beyond the pale of probability. Real interstellar objects like One-Eye Oumuamua and Two-Eye Borisov taught us that such visitors are fragile, often disintegrating or fading without fanfare. Studies in nature astronomy underscore their rarity and the solar system's vast emptiness, making collisions statistical anomalies. For 3i Atlas, every data set from spectroscopic lines showing standard CN and CO emissions to orbital elements with eccentricity, 3.2 supports a peaceful flyby. This extreme speculation serves a purpose. It highlights the robustness of our planetary defenses and the beauty of cosmic serendipity. Tools like the upcoming Near-Earth Object Surveyor mission would provide years of warning for genuine threats, enabling deflections with technologies like hypervelocity projectiles or solar sails. In envisioning these scenarios, we appreciate the delicate balance of the universe where chaos and order dance in harmony. As we ponder these distant possibilities, envision the hypothetical fragments glow, merging with Earth's horizon, a fleeting intersection of worlds. But the authentic 3i Atlas bids us farewell from afar, its legacy, one of knowledge gained clues to planet formation in alien systems, the churn of galactic evolution. In this thought experiment, we find not fear but fascination, knowing that science transforms the unknown into the familiar, one observation at a time. As the quiet rhythm of our cosmic reflection carries us forward, we find ourselves navigating the outer edges of this thought experiment, where the whispers of possibility echo into realms that test the limits of our foresight. The true tale of 3i Atlas unfolds in the present moment of September 2025 as a peaceful interstellar sojourner, its discovery in July marking a moment of astronomical delight rather than dread. Telescopes capture its gentle brightening toward an October perihelion, its tail a subtle streak against the stars, all data affirming a trajectory that bids Earth no more than a distant nod before vanishing into the galactic expanse. Yet within the sanctuary of speculation, we permit our minds to roam freely, conjuring visions of what might transpire if this wanderer, against every scientific prediction, wove itself into the fabric of our world's destiny. This is the pinnacle of what if, a meditative dive into hypotheticals, devoid of evidentiary support, always shadowed by the comfort that reality's script is one of harmony and distance. To extend this imaginative tapestry, let's layer in a scenario where the comet's hypothetical fragment not only impacts but initiates a cascade of unforeseen transformations. In the documented reality, 3i Atlas's composition rich in water, ice, ammonia, and methane, as gleaned from ground-based spectra, suggests a fragile structure that would likely vaporize harmlessly if perturbed. But suppose in this extreme narrative, the fragment survives atmospheric entry intact, its dense core perhaps enriched with silicates from its alien birthplace plunging into a continental heartland. The initial strike at velocities exceeding Mach 100 excavates a basin comparable to Arizona's meteor crater, but scaled exponentially, hurling molten rocks skyward in a plume visible from space. The seismic ripple, registering as a magnitude 10 event on global seismographs, propagates through the planet's crust, awakening fault lines dormant for millennia and triggering aftershocks that reshape landscapes from mountains to plains. Deepening this vision, consider the atmospheric repercussions unfolding over days and weeks. The ejecta cloud, a mix of cometary dust and terrestrial vapor, stratifies into a global haze, scattering sunlight in hues of crimson and gold during sunsets that linger unnaturally long. Temperatures dip worldwide, with polar regions accelerating ice formation and equatorial zones experiencing unseasonal frosts. Agricultural heartlands relying on stable climates face shortened growing seasons, compelling shifts to hardy crops like tubers and grains engineered for resilience. In this what if, the influx of extraterrestrial water vapor, billions of tons from the comet's ices, alters humidity patterns, intensifying storm systems and leading to megafloods in river basins, while arid areas bloom temporarily under anomalous rains. Ecologically, the dust's organic payload could act as a fertilizer, spurring phytoplankton surges in oceans that absorb excess CO2, inadvertently mitigating some climate change effects in an ironic twist of fate. As we probe these unimaginable depths, envision the biological ripple effects. The comet's hypothetical organics, including polycyclic aromatic hydrocarbons, detected in similar bodies like Ryugu via the Hayabusa 2 mission, might integrate into soil microbiomes, fostering new bacterial strains that enhance nutrient cycling, or conversely disrupt existing balances, leading to crop blights. Wildlife adapts. Migratory birds alter routes to avoid dust-laden skies, while marine life thrives on the nutrient boom, potentially leading to overpopulation and ecosystem shifts. Human health enters the equation. Inhaled particulates could exacerbate respiratory issues, prompting global mask mandates, reminiscent of past pandemics, while the psychological toll manifests in a collective awe mixed with anxiety, spurring art, literature, and philosophy centered on our cosmic vulnerability. Pushing the boundaries even further, let's speculate on societal and technological transformations. In the immediate aftermath, communication networks falter under EMP-like pulses from the ionized entry trail, forcing a reliance on analog systems and decentralized grids. Governments mobilize under frameworks like the International Charter on Space and major disasters, coordinating aid via surviving satellites and drone fleets. Innovation accelerates. Space agencies fast-track asteroid mining tech to harvest future visitors for resources, turning peril into opportunity. Economically, markets fluctuate wildly. Insurance sectors collapse under claims, while green tech booms with demands for resilient infrastructure. Culturally, the event could unify disparate societies, fostering global forums on planetary stewardship, or exacerbate divides as resource scarcity fuels conflicts over unaffected regions. To substantiate such extremes in our thought experiment, what evidence would be pivotal? Long-term monitoring, post-impact satellite imagery from Landsat capturing crater evolution, atmospheric sampling by balloons revealing isotopic anomalies from interstellar origins, and genomic sequencing of affected biota showing genetic incorporations. In the absence of these, the scenario dissolves, and fittingly, real-time data from September 2025's James Webb observations depict 3I Atlas as a solitary entity, its volatiles sublimating predictably without fragmentation or deviation. Escalating to truly cataclysmic hypotheticals, imagine the impact coinciding with a solar maximum, amplifying the comet's charged particles to trigger geomagnetic storms that erase data from unshielded drives worldwide, resetting digital civilizations in a blink. Or in a geological twist, the strike penetrates to mantle depths, initiating mantle plumes that birth new volcanic islands over centuries, altering ocean currents and climate epochs. Evolutionarily, the radiation spike from exposed radionuclides in the comet's core could induce mutations, accelerating speciation in isolated populations, perhaps leading to hardier species in irradiated zones. Philosophically, this reshapes humanity's narrative, prompting a post-impact renaissance, where space colonization becomes imperative with lunar bases and Martian outposts prioritized to safeguard our species. Yet even here we must circle back. This is speculation at its most unbound, with no roots in the evidence. Actual analyses from institutions like the Lowell Observatory show 3I Atlas's size and speed render it incapable of such devastation. Most would ablate entirely, contributing mere tons to our atmosphere annually, as with meteoritic input. Probability models in journals like Planetary and Space Science peg interstellar impacts as geological rarities occurring over eons. This imaginative exercise illuminates resilience. Earth has endured far greater, from the late heavy bombardment to the KP extinction, emerging vibrant each time. Human adaptability shines from ancient comet omens in cave art to modern deflection strategies like the 2026 OSIRIS-APEX mission to Apophis. In envisioning these after effects, we honor the scientific method which transforms fear into preparation. As we contemplate this unimaginable aftermath picture, the planet's slow recovery, the dust settling to reveal a sky dotted with new constellations of satellites, humanity gazing upward with renewed wonder. But the genuine 3I Atlas invites no such drama. It's a quiet emissary, its spectra yielding secrets of stellar nurseries, reminding us that the universe's gifts come in whispers, not roars. Through this lens, speculation becomes a tool for appreciation, fostering a deeper bond with the cosmos that cradles us all. As we reach the zenith of this introspective journey through the stars, the veil between the tangible and the theoretical thins to a mere shimmer, inviting us to gaze upon horizons that stretch beyond the ordinary bounds of reason. The authentic chronicle of 3 Atlas, as it stands in the crisp air of September 2025, is one of understated elegance, a comet unearthed by the Atlas Survey in July. Its path a swift embrace of the sun before an eternal farewell, with observations confirming its interstellar pedigree through hyperbolic metrics and spectral fingerprints of distant origins. No closer than the vast gulf of space allows it fades now into the night, a natural envoy bearing no malice, only mysteries of the galaxy's ancient forge. Yet in the sanctuary of our thought experiment, we dare to ascend to the ultimate speculative peaks where what if evolves into visions of profound alteration. What if 3I Atlas, in a confluence of cosmic improbabilities, transcended mere impact to become a catalyst for planetary rebirth? This pinnacle of conjecture stands apart from all evidence, a poetic musing that honors the universe's vast potential, while reaffirming that real data paints a portrait of tranquility and transience. To crown this speculative edifice, let's weave a narrative where the comet's hypothetical descent spirals into a symphony of global metamorphosis. In the verified annals, 3I Atlas's nucleus, modestly sized and icy, would pose little more than a spectacular light show if somehow redirected, a fate dismissed by orbital certainties from NASA's vigilant eyes. But envision in this extreme tableau the object not fragmenting, but coalescing under unforeseen pressures, its ices compressing into a denser form during solar proximity, perhaps through hypothetical phase transitions unobserved in nature. This transformed body, now a hybrid of ice and rock, barrels toward Earth, with unyielding momentum, its entry not a fiery demise, but a burrowing plunge into the mantle facilitated by an imagined structural integrity defying cometary norms. The initial breach piercing the crust like a cosmic lance vents superheated gases that mingle cometary volatiles with terrestrial magma, birthing hybrid eruptions that repaint the skies in iridescent veils. Delving into this ultimate what-if, picture the geological renaissance that ensues. The impact site, a caldera of unprecedented scale, becomes a nexus for tectonic renewal, Fault lines realign as shock waves propagate, easing pressures along subduction zones and potentially averting future megaquakes in regions like the Pacific Ring. Volcanic plumes enriched with interstellar silicates deposit fertile ash across continents, rejuvenating depleted soils and sparking agricultural revolutions in once barren lands. Climatically, the aerosol injection initiates a balanced cooling countering anthropogenic warming by a precise degree, as if the universe conspired to restore equilibrium. Oceans infused with cometary water, bearing deuterium ratios alien to Earth, dilute salinity in key basins, revitalizing coral reefs and fostering marine biodiversity explosions, new species emerging from genetic admixtures where extraterrestrial organics catalyze evolutionary leaps in plankton and fish alike. As the speculation soars to ethereal heights, consider the atmospheric alchemy at play. The comet's tail in this fantastical close encounter drapes Earth in a temporary shroud of ionized particles, interacting with the ionosphere to enhance auroral displays into perpetual spectacles that illuminate nights worldwide. This charged envelope could amplify radio propagation, revolutionizing communications by enabling natural signal boosts that render satellites obsolete in some spectra. Environmentally, the organic influx molecules like glycine and purines hinted at in real cometary analyses from missions like Stardust Seeds, the biosphere with building blocks accelerating bioremediation in polluted zones. Imagine toxic waste sites blooming with hyper-efficient microbes that devour plastics and heavy metals, a gift from the stars hastening ecological recovery. Pushing toward the sublime extremes, let's hypothesize societal transfigurations born from this event. In the wake of the gentle cataclysm, more renewal than ruin, humanity unites under a banner of cosmic humility, establishing global observatories dedicated to interstellar vigilance, funded by redirected military budgets. Technological leaps abound, reverse engineering the comet's resilient structure inspires metamaterials for spacecraft, enabling faster than ever probes to neighboring stars. Culturally, art and spirituality flourish. New religions emerge venerating the celestial harbinger, while literature explores themes of interconnected fate, drawing from ancient comet lore in texts like the Epic of Gilgamesh. Economically, the mineral riches unearthed from the crater, perhaps rare earths fused in alien forges, fuel a green energy boom, with fusion reactors powered by isotopic anomalies, providing limitless power. Biologically, the ultimate speculation unfolds in human evolution itself. Exposure to low-level radiation from the comet's core in this imagined scenario induces subtle epigenetic changes, enhancing cognitive resilience or longevity in exposed populations, echoing theories of radiation hormesis studied in labs today. Diseases wane as novel compounds integrate into pharmacology, curing ailments through interstellar chemistry. Philosophically, the event redefines existence. Humanity now. Star Touch pursues a multi-world destiny with fervor, colonizing Mars with technologies born from the encounter, ensuring survival against future wanderers. But to tether this flight of fancy, what evidence would demand such a narrative? Profound multidisciplinary proofs, geological cores revealing fused extraterrestrial-terrestrial strata, genomic databases showing widespread mutations traceable to cometary signatures, atmospheric models correlating cooling trends with isotopic spikes. None of these align with reality. September 2025's data from the European Space Agency's Comet Interceptor planning underscores 3I Errantless as fragile and for its volatile standard its path irrevocable. This zenith of speculation, while exhilarating, underscores the improbability interstellar objects like 3I Atlas are galactic drifters, not agents of change, with impact likelihoods dwarfed by everyday risks, as per assessments from the B612 Foundation. Real studies reveal comets as porgy aggregates disintegrating under stress, contributing benignly to our atmosphere's water budget over eons. In embracing these ultimate horizons, we see the universe not as adversary, but ally its mysteries inviting exploration. The hypothetical rebirth fosters appreciation for our planet's tenacity, having weathered cometary barrages in its youth to birth life. Humanity's response innovation unity mirrors our history of rising from ashes. As we crest this speculative summit, visualize Earth's renewed face, greener fields under softer skies, humanity starward bound. But the true three-eye atlas offers subtler wonders, its spectra unveiling galactic chemistry, its orbit a lesson in cosmic motion. In this thought experiment's close, we find solace. The universe's strangeness yields to understanding one serene observation at a time, guiding us toward harmony with the infinite. As the echoes of our speculative explorations fade into the quiet vastness, we begin to turn our gaze inward toward the human story woven into this cosmic narrative. The tale of Three-Eye Atlas in its true form as observed in the clear nights of September 2025 is one of gentle departure, a comet that brushed our solar system with light and left us with data to ponder its interstellar origins, confirmed by spectra and orbits that speak of natural wonders far beyond our reach. No closer encounters, no dramatic shifts. Just a visitor that expanded our horizons without a whisper of threat. Yet having ventured through the realms of what if, where this ancient traveler might have drawn near or even touched our world, it's time to reflect on how we as a species might respond. This shift brings us to the human element, the reactions, the challenges, the delicate dance between curiosity and caution. Always we hold fast to the reality Three-Eye Atlas was and is a safe spectacle, its path a testament to the predictability of the cosmos. Imagine then, in the wake of such a hypothetical event, whether a close flyby or the more extreme scenarios, we've pondered the first waves of human reaction rippling across the globe. It would begin with awe, that primal emotion stirred by the stars. Social media platforms like X would light up with images and videos, hashtags like Dakshun Atlas arrival trending, as people from bustling cities to remote villages share their glimpses of the glowing intruder. Amateur astronomers armed with backyard telescopes would become overnight storytellers, their live streams drawing millions into a shared moment of wonder. In observatories, scientists would work tirelessly, their data feeds becoming public lifelines, demystifying the object with real-time updates on its composition and trajectory. This initial surge of fascination mirrors historical events like the 1910 passage of Halley's Comet, when crowds gathered in fear and excitement, blending myth with emerging science. But in our modern era, with instant connectivity, the response would be amplified, a global conversation unfolding in threads and posts uniting diverse voices in a tapestry of curiosity. Yet beneath the wonder, threads of concern would weave in, shaping a more complex reaction. Governments and space agencies drawing on protocols from organizations like NASA's Planetary Defense Coordination Office would activate monitoring teams issuing calm briefings to assure the public of safety. In this thought experiment, if early data suggested even a remote chance of impact, press conferences would emphasize probability, stressing that the odds remain astronomical, much like the 1 in 45 thousand chance once assigned to asteroid Apophis before refinements dismissed it. Public figures from presidents to influencers would call for unity, echoing sentiments from past crises where humanity rallied. Schools might integrate the event into curricula, teaching children about orbital mechanics through interactive apps, fostering a generation of stargazers. Community gatherings, star parties in parks, virtual reality simulations of the comet's path would transform fear into education, reminding us that knowledge is our greatest shield. As reactions deepen, political challenges would emerge, testing the fabric of international cooperation. Space is a domain without borders, yet responses to celestial events often reveal earthly divides. In our speculative scenario, nations with advanced observatories like the United States, with its Hubble legacy, or China, with the fast radio telescope, might lead data sharing, but tensions could arise over resource allocation. Who funds deflection missions if needed? The Artemis Accords, a framework for lunar exploration, could extend to comet defense, but debates in the United Nations might stall over equity developing countries, arguing for technology transfers to ensure global preparedness. Historical precedents, such as the 1986 International Halley Watch that united 20 nations, show collaboration is possible, yet politics could complicate it. Imagine summits where leaders balance national security with shared humanity, perhaps forming a new treaty on interstellar threats, emphasizing that the stars belong to all. Social challenges would mirror these amplifying voices from the margins. In a world still healing from pandemics and conflicts, a cosmic visitor could exacerbate inequalities, rural communities without dark skies, or internet access feeling isolated from the spectacle, while urban dwellers grapple with misinformation. Conspiracy theories might proliferate on platforms like Reddit, claiming artificial origins despite spectroscopic evidence of natural ices and organics. Social scientists, drawing from studies on disaster psychology, would note how such events trigger existential reflection, leading to movements for environmental stewardship or space migration. Mental health support would become crucial, with hotlines addressing cosmic anxiety, a term for the unease of contemplating our smallness. Yet positivity could prevail. Artists inspired by the comet's glow create murals and music, while philanthropists fund scholarships in astronomy, bridging social gaps through shared skyward dreams. Balancing curiosity and safety forms the core of this response, a delicate equilibrium humanity has navigated since Galileo's telescope. In the hypothetical close approach, scientific curiosity would drive missions, perhaps a hastily launched probe, like the 2005 Deep Impact sampling the Comet for interstellar secrets. The allure of knowledge unlocking clues to planet formation or life's building blocks would fuel advocacy from bodies like the International Astronomical Union. Yet safety measures would temper this, evacuation plans for potential impact zones, stockpiling essentials, and ethical debates on deflection ethics. Should we alter a natural object's path or let the cosmos run its course? Philosophers might invoke the precautionary principle, weighing the thrill of discovery against risk, much like bioethicists debate gene editing. In this balance, innovation thrives. Private enterprises like SpaceX could deploy satellite constellations for real-time tracking, while AI algorithms predict trajectories with unprecedented accuracy. Public engagement tools, apps simulating what-if scenarios, educate without alarming, fostering informed curiosity. Socially, this equilibrium challenges biases, ensuring diverse representation in STEM fields, where women and minorities lead comet studies, enriching perspectives. As we reflect, humanity's response reveals resilience. From ancient comets seen as omens to modern ones as opportunities, we've evolved from fear to fascination. In reality, 3i Atlas elicited just that: global stargazing. Without strife, its data shared freely via open access journals. Political hurdles like funding disparities highlight needs for equity, while social dynamics underscore connectivity's power. Balancing curiosity with safety ensures progress, exploring without recklessness, as in the OSIRIS-REx mission's asteroid sample return. This human chapter, even in speculation, affirms our capacity for wonder and wisdom. As 3i Atlas recedes in truth, it leaves a legacy of unity, reminding us that in facing the unknown, we find our strength. As we continue to unravel the human dimensions of this cosmic encounter, the reactions we've explored, from shared awe to the intricate web of political and social challenges, reveal how deeply intertwined we are with the stars above. In balancing our innate curiosity with the imperative of safety, humanity demonstrates its capacity to confront the unknown, not with panic, but with thoughtful deliberation. This equilibrium, forged in the crucible of speculation about Three-Eye Atlas, invites us to broaden our perspective even further, stepping back to contemplate the immense scale of the universe itself. Here in this expansive view, the story of one interstellar wanderer becomes a mere footnote in a grander narrative, one that humbles us while igniting hope through the lens of science. Remember, as always, our foundation remains rooted in the real three Atlas observed in the tranquil skies of September 2025 is a natural object on a safe outbound path. Its data, a gift that expands our knowledge without any hint of peril. To grasp the true magnitude of the universe, let's begin by zooming out from our solar system, that familiar bubble of planets and comets orbiting a single star. Our sun is but one of over 200 billion stars in the Milky Way, a galaxy spanning 100,000 light-years a distance so vast that light itself traveling at 186,000 miles per second takes a century to cross it, and the Milky Way. It's just one of perhaps 2 trillion galaxies in the observable universe, each teeming with stars, planets, and wandering objects like Three-Eye Atlas. This scale defies comprehension. If you shrank the observable universe to the size of Earth, our galaxy would be a speck smaller than a grain of sand. In this immensity, interstellar visitors are inevitable, ejected from distant systems. By gravitational slingshots, they drift through the void, crossing paths with other stars every few million years. Three-Eye Atlas, with its hyperbolic orbit clocked at speeds that carry it beyond our grasp, exemplifies this galactic exchange, a reminder that our solar system is not an island, but a port in a cosmic sea. Within this vastness, Earth's place is both insignificant and profoundly unique. Our planet, a rocky world with liquid water and a protective atmosphere, has broadcast its presence unwittingly for over a century through radio signals. Since the first transmissions in the early 1900s, think Marconi's experiments or the advent of commercial radio, these electromagnetic waves have rippled outward at the speed of light, forming an expanding sphere, now about 200 light-years in diameter. Shows like I Love Lucy, news broadcasts, and even radar pings from World War II echo into space, potentially detectable by any advanced civilizations within that bubble. In our thought experiment about Three-Eye Atlas drawing near, one might wonder if such signals could have attracted it like a beacon in the dark. But science dispels this notion. Radio waves weaken over distance, becoming indistinguishable from background noise after a few light years without targeted amplification. Moreover, Three-Eye Atlas as a natural comet responds only to gravity and physics, not to our cultural artifacts. Real data from SETI initiatives scanning for extraterrestrial signals find silence in the cosmos thus far, underscoring that if intelligent life exists, it's likely as isolated as we are in this sprawling expanse. This scale also illuminates the rarity of events, like a hypothetical close encounter with Three-Eye Atlas. The interstellar medium is sparse, about 1 atom per cubic centimeter, meaning objects like this comet traverse emptiness for eons, their paths dictated by chance alignments of stars and planets. Estimates from astronomers at the Harvard-Smithsonian Center for Astrophysics suggest that interstellar objects pass through our solar system at a rate of 1 detectable every few years, but collisions. Those are geological footnotes occurring perhaps once every 100 million years. Our planet bears scars from such rarities, the Chicxulub crater from 66 million years ago, which altered life's course, but these are from solar system debris, not interstellar nomads. In the context of Three-Eye Atlas's real trajectory, mapped with precision by telescopes like the Very Large Array, the odds of deviation are negligible, offering hope that the universe's scale acts as a buffer, diluting dangers across infinities. Yet from this vastness springs hope drawn from the very data that Three-Eye Atlas and its kin provide. Each observation peels back layers of the cosmos, revealing patterns that make the unknown less daunting. Spectroscopic analysis of 3I Atlas's coma, capturing emissions from water and carbon compounds, mirrors those in distant nebulae observed by the James Webb Space Telescope, suggesting universal recipes for star and planet birth. This continuity breeds optimism. If the same laws govern everywhere from Newton's gravity-shaping orbits to quantum mechanics and stellar fusion, then we can predict, understand, and even harness the stars. Hope emerges too from our growing ability to monitor the skies. Surveys like the Legacy Survey of Space and Time, set to map billions of objects, will spot future visitors years in advance, turning potential threats into scientific bonanzas. In reflecting on Earth's radio signals amid this scale, we see a dual-edged sword. They announce our existence, yet in the universe's immensity, they are whispers lost in a roar. Projects like Breakthrough listen, scan for replies, finding none yet, which could mean we're alone or simply that distances mute conversations. This solitude fosters hope through self-reliance. Humanity must steward its own fate, advancing technologies like solar sails or fusion drives to explore beyond. In our speculative lens, a close 3 atlas might accelerate the spurring investments in space, but reality's data already propels us. Samples from asteroids like Bennu returned by OSIRIS-REx show life's ingredients are common, hinting at a fertile cosmos. The universe's scale also invites philosophical solace. In its grandeur, our problems shrink. Conflicts over borders pale against galactic arms. 3I Atlas, as a messenger from afar, embodies this. Its journey spanning light years connects us to the Big Bang's echoes, reminding us we're stardust animated by the same forces. Data from cosmic microwave background maps like those from Planck show a universe fine-tuned for complexity, offering hope that wonder awaits discovery. As we ponder this expanse, visualize the Milky Way's spiral. From a mountaintop stars a river of light. Earth's signals, faint but persistent, symbolize our reach, curious tendrils into the void. Hope from data lies in patterns, predictable orbits, shared chemistries, a cosmos inviting inquiry. This vast perspective tempers our reactions to hypothetical threats, emphasizing preparation over fear. Political challenges yield to global accords, social divides to shared skies. In the universe's scale, 3I Atlas is a spark igniting curiosity that binds us. As we expand our view to encompass the boundless scale of the universe, where galaxies swirl like leaves in an endless wind, and Earth's radio whispers fade into the infinite silence, we find a profound sense of hope blooming from the data itself. This hope isn't born of wishful thinking, but from the meticulous observations that reveal patterns, predictability, and a cosmos ripe for understanding. In the story of 3I Atlas, whether viewed through the lens of its real harmless passage or the speculative paths we've wandered, we see humanity's reactions evolving from initial wonder to collaborative resolve, navigating political and social currents while balancing our thirst for knowledge with the wisdom of caution. Now, as this narrative begins to draw toward its close, let's gently bid farewell to this interstellar visitor, reflecting on the scientific treasures it has bestowed upon us. Even in imagination, 3I Atlas serves as a bridge to deeper insights, expanding our grasp on the formation of planets and the evolution of galaxies. And through it all, the message resonates: the universe, for all its wonders and mysteries, is a realm we can comprehend one starlit step at a time. Let's start this farewell by revisiting the quiet departure of 3I Atlas in the real world as it unfolds in the skies of September 2025. Having swept past its perihelion, the comet now recedes, its tail dimming like the last notes of a symphony fading into night. Telescopes track its outbound arc, a hyperbolic curve that carries it beyond the outer planets, destined for the interstellar void from whence it came. No dramatic finale, no lingering threats, just a graceful exit that leaves astronomers with reams of data to sift through for years. This goodbye is serene, a cosmic adieu that underscores the transience of such visitors. In our thought experiment where we've imagined closer brushes or even transformative encounters, this farewell takes on added poignancy, a reminder that even in the most extreme what-ifs, the object eventually moves on its influence, waning as distance reclaims it. Visualizing this picture, the comet as a fading light on the horizon, its glow merging with the star field, a silent promise that the universe continues its eternal dance. In bidding farewell, we turn to the invaluable scientific legacy. 3I Atlas imparts a treasure trove that enriches our understanding of planetary formation. Comets like this are time capsules, preserving the raw materials from the dawn of star systems. Spectroscopic data from its coma captured by instruments like the Hubble Space Telescope reveal a cocktail of water, ice, carbon dioxide, methane, and organic molecules, the very building blocks that coalesce into planets. By comparing these with solar system comets, scientists discern subtle differences, perhaps a higher abundance of certain isotopes, hinting at formation in a cooler, more distant stellar nursery. This expands our knowledge of how planets assemble disks of gas and dust around young stars, clumping into worlds with comets as leftover debris ejected into space. Real studies of objects like 2I Borisov have shown similar compositions, suggesting that planet-building processes are universal, occurring in myriad ways across the galaxy. 3I Atlas adds to this mosaic, its data helping model protoplanetary disks observed in regions like the Orion Nebula, where new stars and planets are born amid glowing clouds. This scientific value extends to the mechanics of ejection and travel, illuminating how such objects become interstellar nomads. Gravitational simulations trace 3RI Atlas's backstory, likely perturbed by a massive planet in its home system slingshot into the void billions of years ago. This process mirrors the formation of our own Oort cloud, a reservoir of icy bodies at the solar system's edge, occasionally nudged inward as comets. By studying its trajectory, refined through astrometric measurements from Gaia, the comet teaches us about galactic dynamics, how stars' motions scatter debris like cosmic confetti. This knowledge refines models of planet formation, showing that systems with giant planets like Jupiter are efficient at ejecting material, potentially influencing habitability by clearing hazardous orbits. In essence, 3I Atlas is a probe from another era, its scarred surface darkened by cosmic rays, bearing witness to the harsh interstellar environment where radiation and sparse collisions shape survivors over eons. Moving deeper, the comet's legacy touches on galactic evolution, the slow, majestic transformation of the Milky Way over cosmic time. Interstellar objects like 3I Atlas carry chemical fingerprints of their birthplaces, offering snapshots of stellar chemistry at different epochs. For instance, its metallicity, the abundance of elements heavier than helium, might be lower than our sun's, suggesting origin around an older metal-poor star. This data, combined with surveys from the James Webb Space Telescope peering into ancient galaxies, helps chart how the galaxy enriches itself, supernovaing, forging heavy elements, dispersing them into gas clouds that birth new stars and planets. 3I Atlas. As a wanderer connects these dots, showing material exchange between systems, a galactic recycling that evolves structures from loose associations to spiral arms teeming with life potential. Evolutionary models informed by such visitors predict how galaxies mature, merging and growing over billions of years, with rogue objects as tracers of this history. In this farewell, the hopeful message emerges naturally. The universe, though brimming with enigmas, adheres to discoverable laws, granting us the power to understand and perhaps even shape our place within it. Data from 3I Atlas reinforces this. Its predictable orbit, governed by gravity's unyielding equations, assures us that chaos has order. This understanding brings peace, transforming the night sky from a realm of fear to one of invitation. Humanity's cooperative spirit, seen in global telescope networks, sharing observations, mirrors this. We collaborate to decode the stars just as we might in facing real challenges. The comet's scientific yield, expanding knowledge on formation processes, fuels optimism for future discoveries like habitable exoplanets or signs of distant life pursued through missions like the Habitable Worlds Observatory. As we say goodbye, let's linger on the poetic three-eye atlas as an ancient wanderer, a messenger bearing tales of far-off births and journeys. Its value lies not in drama, but in quiet revelation, broadening our cosmic vocabulary. The hopeful thread, in comprehending such wonders, we find unity and purpose, a shared quest that transcends borders. The universe is marvelous, yet malleable to our minds, a canvas where science paints serenity. This parting reflection sets the stage for closure, where the lessons of Three-Eye Atlas linger, inspiring us to look upward with eyes wide in wonder and hearts steady in knowledge. As we tenderly bid farewell to Three-Eye Atlas, watching its ethereal form blend into the star-strewn backdrop of the night, we carry forward the profound scientific insights it has gifted us, clues to the intricate dance of planetary birth and the slow, majestic unfurling of galactic arms. This knowledge gleaned from spectra and orbits not only broadens our intellectual horizons, but also weaves a thread of continuity between our world and the distant stellar forges that birth such wanderers. In this moment of reflection, as the comet's legacy settles into the annals of astronomy, we turn our thoughts to the deeper philosophical undercurrents stirred by its passage. The universe, in its boundless expanse and rhythmic predictability, prompts us to ponder our existence, our fears, and our aspirations. Through the lens of science, what once seemed a source of dread transforms into a wellspring of serenity, reminding us that the cosmos, though strange and vast, operates by principles we can grasp, fostering a quiet confidence in our ability to navigate its mysteries together. Let's delve into this philosophical tapestry, beginning with the interplay between science and speculation that Three-Eye Atlas so elegantly embodies. Science grounds us in evidence, the measurable, the repeatable, while speculation invites us to explore the edges of possibility, much like a dreamer gazing at the horizon. In the real journey of Three-Eye Atlas, discovered in the summer haze of July 2025 by the Atlas Survey, its hyperbolic path and cometary activity provided a canvas for both. Observations from Hubble and Webb telescopes revealed a nucleus wrapped in a dusty cocoon, its composition a mix of ices and organics that echo the building blocks of worlds. This factual foundation dispels wild fancies, yet our thought experiment, imagining altered trajectories or dramatic encounters, serves a purpose. It sharpens our scientific tools, preparing us for genuine anomalies. Philosophically, this duality teaches humility. We acknowledge the limits of knowledge while celebrating the human spirit's urge to wonder. As thinkers like Carl Sagan noted, speculation, when tethered to science, becomes a ladder to truth, not a drift into delusion. This balance addresses our innate fear of the universe, that primal shiver when contemplating the void. Ancient cultures saw comets as omens of doom, harbingers of change etched in the sky. In modern times, with Three-Eye Atlas streaking through our solar system at speeds that defy earthly bounds, similar echoes might arise, whispers of existential threat amid the awe. Yet science offers constellation data from its trajectory, calculated with precision, down to kilometers, shows no peril, its closest brush with Earth, a distant 1.8 astronomical units. This assurance transforms fear into fascination. The universe isn't a hostile arena, but a neutral expanse governed by impartial laws. Philosophically, this shift echoes existentialism's call to find meaning in an indifferent cosmos. We craft our purpose through inquiry and connection. The comet's safe passage reassures us that while the stars may seem cold, our understanding warms them, turning potential dread into a comforting embrace of the known. Deeper still, Three Eye Atlas invites triptych reflections on our cosmic philosophy, our place in the grand scheme, the interplay of chance and order, and the ethical imperatives of exploration. First, our position. Earth, a speck in the Milky Way's swirl, hosts life that ponders its origins. The comet ejected from another star system perhaps billions of years ago underscores our interconnectedness. Materials from distant realms mirror those in our bones, a stardust lineage that binds us to the galaxy. This perspective fosters a sense of belonging, not isolation. We're participants in a universal story, as data from its isotopes might reveal shared chemical histories with exoplanets spotted by telescopes like Kepler. Second chance versus order. The comet's arrival, a probabilistic fluke in the vast emptiness, highlights randomness, yet its motion obeys gravity's elegant equations. This duality suggests a cosmos where chaos bursts complexity, much like how quantum fluctuations seeded the Big Bang structure. Philosophically, it encourages optimism. If order emerges from chance, so too can harmony from human endeavors. Third, the ethics of our cosmic gaze. As we study objects like Three Eye Atlas, we confront responsibilities. Should we intervene if a future visitor poses risk-altering nature's course? Our thought experiment explored deflections, raising questions of stewardship, preserving our world while respecting the universe's integrity. Data-driven decisions like those in planetary defense simulations guide us toward ethical balance, emphasizing collaboration over conquest. This philosophy extends to broader exploration missions. Sampling interstellar objects could unlock life's secrets elsewhere, but with care to avoid contamination, honoring the pristine nature of cosmic artifacts. The educational value of Three Eye Atlas shines here, transforming philosophy into practical wisdom. Classrooms worldwide could use its data nucleus estimates from Hubble spectra, from Webb, to teach orbital mechanics and chemistry, inspiring young minds to see the universe not as abstract, but accessible. Public outreach through apps tracking its path or virtual reality tours of its journey democratizes knowledge, bridging gaps between experts and enthusiasts. Philosophically, this empowers us against misinformation. By emphasizing evidence, we cultivate critical thinking, turning speculative fears into informed discussions. The comet's legacy educates on resilience, too. Earth has weathered cosmic visitors before emerging stronger, a lesson in adaptability. Woven through these reflections is a message of positivity, science as a beacon of peace. In dissecting Three Eye Atlas's coma, or modeling its ejection, we find patterns that demystify the strange, revealing a universe that, while wondrous, follows rules we decipher. This understanding breeds tranquility. Fears dissolve in the light of data, replaced by the joy of discovery. Humanity's cooperative essence, scientists sharing observations across borders, mirrors this, showing we can unite to comprehend the stars. The cosmos becomes a partner in our quest, its marvels inviting us to explore, with hope, not hesitation. In this philosophical embrace, visualize the universe as a vast library. Three Eye Atlas, a borrowed volume, returned to the shelves, its pages enriching our story. The insights linger, guiding us toward a future where knowledge illuminates the path, fostering peace in the face of infinity. As we embrace the philosophical depths stirred by Three Eye Atlas, where science tempers speculation, fear yields to understanding, and our cosmic philosophy reveals a universe of interconnected wonder, we arrive at the gentle culmination of this narrative. The comet's passage, whether in its factual distant glide or the imaginative realms we've traversed, has illuminated not just the mechanics of the stars, but the essence of our humanity, our capacity to question, to collaborate, and to find meaning in the vast unknown. Now, as the final threads of this story converge, let's draw together the lessons learned, reaffirming the scientific value that expands our knowledge of planetary formation and galactic evolution. In this closing reflection, we extend a heartfelt farewell to our cosmic traveler, carrying forward a message of hope. The universe is indeed marvelous, filled with strangeness and splendor, yet it unfolds according to principles we can unravel, empowering us to face its mysteries with open hearts and united minds. Let's begin this conclusion by weaving back to the core themes that have guided us, synthesizing the journey from discovery to speculation and back to reality. The introduction of 3I Atlas, that faint streak in the telescopes of 2023, sparked a chain of inquiry that mirrored humanity's eternal dialogue with the cosmos. We described its interstellar origins, emphasized its natural trajectory through evidence from spectra and orbits, and ventured into thought experiments that escalated from subtle perturbations to extreme transformations. Through it all, we returned faithfully to the data observations from Hubble Webb and ground-based arrays that confirm its benign nature, a comet unbound and outbound as of September 2025. This structure, like a documentary unfolding chapter by chapter, has built tension through what-ifs, only to resolve in reassurance, much as the universe itself builds galaxies from chaos into ordered spirals. Philosophically, this mirrors life's own arc, beginnings in mystery peaks of intensity and endings that offer wisdom and peace. In this synthesis, the human response stands as a testament to our growth. We discussed how awe would give way to organized action, with political challenges forging stronger international bonds and social dynamics, highlighting our shared vulnerability and strength. The vast scale of the universe, with its trillions of galaxies and Earth's faint radio echoes, placed our story in context, reminding us that isolation breeds not despair, but opportunity for self-discovery. Bidding farewell, we celebrated the scientific bounty insights into how protoplanetary disks eject wanderers like 3I Atlas, shaping systems where planets form amid dust and gas. This knowledge evolves our view of the galaxy from a static backdrop to a dynamic entity where stars merge, elements, cycle, and life potential scatters like seeds. The philosophical embrace deepened this, showing science as the antidote to fear, education as the bridge to unity, and positivity as the fruit of understanding. Now, as we prepare to part ways with 3I Atlas, let's linger on its final gifts, emphasizing the expansive scientific value that propels us forward. Beyond immediate data, this comet contributes to long-term models of planetary formation. Imagine the early solar system as swirling disk where gravity clumps particles into planetesimals, then planets with leftovers frozen as comets. 3I Atlas, with its foreign isotopes, perhaps a higher deuterium content detected in its water vapor, suggests variations in this process across stars. This informs simulations run on supercomputers at institutions like NASA's Ames Research Center, predicting how different stellar masses yield diverse worlds, hot Jupiters around massive stars, or Earth-like rocks in habitable zones of Sun-like ones. By studying its organics, simple carbons that might seed atmospheres, the comet hints at how life's precursors migrate, supporting theories like panspermia without invoking the extraordinary. In reality, as 3I Atlas fades from view, its archived spectra in databases like the Planetary Data System will fuel dissertations and discoveries for decades, each analysis a step toward mapping the galaxy's habitable niches. This value cascades into galactic evolution, where 3I Atlas serves as a probe of cosmic history. Galaxies evolve through mergers and starbursts, enriching gas with metals forged in stellar cores. The comet's composition, analyzed through infrared signatures, might reveal a snapshot from a younger, less enriched epoch, helping astronomers trace the Milky Way's growth from a dwarf galaxy to its current grandeur. Data from its dust particles scattered by outgassing mirrors, those in interstellar clouds observed by the Spitzer Space Telescope's successors, showing how material recycles, supernovae disperse elements, clouds collapse into stars, and ejections like 3I Atlas carry them afar. This understanding refines cosmological models linking small-scale events like comet ejections to large-scale structures such as the cosmic web of filaments where galaxies cluster. Philosophically, it affirms a universe in motion where evolution isn't random, but patterned, offering hope that we can forecast its future, perhaps predicting the Andromeda collision billions of years hence. In this farewell, the hopeful message crystallizes. The universe is a tapestry of marvels, strange in its scale, and surprises yet comprehensible through the lens of science. 3 by Atlas exemplifies this. Its arrival a strange visitor from the void, its study a triumph of human ingenuity. Science brings peace by revealing order, gravity's pull, chemistry's bonds, evolution's paths, all decipherable, all reassuring. This comprehension empowers cooperation. As we've seen in global responses to celestial events from the International Space Station to shared comet watches, humanity unites when facing the stars. The message is one of optimism in a cosmos that birthed consciousness. From dust wonders await those who seek with open minds. Fear of the unknown dissolves in discovery's light, replaced by the joy of belonging to something greater. As we conclude, visualize one last scene standing under a starlit sky, the faint trace of 3i Atlas lost among the constellations, yet its essence lingers in our thoughts. This journey from introduction to speculation to reflection leaves us wiser, more connected. The comet departs, but its lessons endure scientific expansion, philosophical depth, and a hopeful embrace of the marvelous, understandable universe. In this spirit, we look forward ready for the next cosmic whisper hearts alight with possibility.